Hey everyone, I'm Everett Hildenbrandt, and Grigory Roshu, our CEO, is also here, so say hi to him as well. Today I'm talking about formal verification of Foundry tests, which is an ambitious title. So this is what a Foundry test looks like. You have, there's a link to this example. You have some sort of setup function which allows you to initialize your scenario, and then you have functions that are prefixed with tests that can take in parameters like this. And Foundry will basically fuzz over these parameters and run your test with, a bunch of different values of the parameters. What Joran was just talking about. Actually, Foundry is really nice because it doesn't really instrument the contracts or anything like that. It instruments the runtime instead, but in a minimal way. So starting from blank state, execute the setup function, get a state, and then use that to execute each of your tests with different parameters for input. These Foundry tests can get really big very quickly. I guess I can't click on this. This is an example of a large suite of Foundry property tests, but they can actually describe pretty complex behaviors with, complicated deployment schemes that need to be described, and then lots of tests that each individual property that's important for your protocol is holding, basically. Sorry. Come on. So these can get big. Foundry allows fuzzing, which you just do with forge test. And so here I just had some simple test suite that I fuzzed over. So here you can see it's calling like the test withdraw function, but it doesn't have any parameters. And so it just runs it once and that's it. But here you have test withdraw fuzz, which takes in a uint96, and it ran it 256 times on different input values to make sure that the test is holding, right? Same with these prank tests. The key things about Foundry is, this lots of runs thing, and that it's super fast, right? And I'll talk a little bit about the speed in a second here, but you might not think it's important, but it is important. HEVM is a different symbolic execution engine that actually already supports Foundry tests because Foundry inherited a lot of good design decisions from a suite of tools called DApp tools. And we are basically following the HEVM path. We have this KVM Foundry to K command, which will basically generate all of the K specifications needed for a given Foundry test suite. So these can get quite big. I had a very simple test suite. It ended up being 23,000 lines of K code. Obviously, you don't want to write all those specifications by hand, right? And this is what an example specification looks like here. So, it's massive. But you obviously don't want to write all this by hand, so that's what the Foundry to K tool does for you. Once you've generated your K specifications with Foundry to K, you need to compile them. So that's to translate your K specifications to core, which is machine-readable matching logic. Matching logic is the deductive verification framework we use for discharging our proof obligations. This is a fixed amount of time. It's always going to be about 2 minutes, basically. Then you need to discharge the KVM specifications. So there were 55 specifications there that were generated. You have to call KVM prove on the specifications to discharge them. If you're lucky, or if your tests are right and your code is right, you get something back that says true. But if you're unlucky or your code is wrong, you get something back that looks like this, and then you have to call up an expert, or you have to become an expert in K in order to do this. The times here can vary wildly. They're going to depend on the properties you're verifying and the complexity of your code, basically. So the current work right now is we're implementing the remaining cheat codes. Foundry has this notion of cheat codes. That's the instrumented runtime I was talking about. Right now we support one cheat code, but we have pull requests open for supporting the next 8 most popular ones. We need to support the setup function. I think that'll take a few weeks, and then we need to improve performance. I'm going to give you a sneak peek about some performance numbers that we've been working on for concrete execution, and I've included Foundry's times here for your guys' reference. Foundry claims to be, I haven't seen any data on this, but Foundry claims to be really fast. And so here's Foundry's time to execute like the sum to 2. This is just a program that counts 1 to 2 and adds them up, or 1 to 20 adds them up, right? So Foundry is taking, 364 microseconds to sum to 2, but is taking 10 seconds to sum to 20 million. Our KVM on the same tests is taking these times right here, right? And so you can see that is what, like 3 or 4 orders of magnitude slower. But we have this exciting new performance improvement that we're rolling out in the next few months to all of our case semantics, not just our EVM semantics, that gives us a 2 orders of magnitude improvement in performance. So we're actually now only 1 order of magnitude slower than Foundry, which puts us in the realm of being the same performance bracket as several other clients on the network. I don't know if Foundry's claims of being the fastest are actually true. I didn't validate that. Another thing that's important is that this performance improvement that we see here, this 2 orders of magnitude performance improvement using this semantics-based compilation, actually translates to symbolic execution as well. And so we can, I mean, the numbers here are a little more scattered, but you can see basically the same. We can get out to sum to 1,000 using symbolic execution in the same amount of time that it took to sum to 10 instead. So that's kind of cool. You want to get involved? Install KVM. Try out this presentation's instructions. Go to kframework.org and do the K tutorial. It's taking a lot of people about 2 weeks. There's our Discord. We have a Twitter, RV Inc. We have a blog where we'll be announcing when we finish up these cheat codes. We'll also be announcing any of the performance improvements that come. And big thanks to Stanford, Satora, and Lori for putting up with my late emails. So thanks, everyone.